So without further ado,
Thank you very much, Phil. Thank you very much for inviting me to do this seminar, and to all of you for having me here again. So thanks very much. It's a delight. I'm enjoying myself, and time is going far too quickly as tiny little packing figure. But we're having a good time. So today I'm talking about, can everybody hear me? I'm talking about developmental research, which is about inquiry in mathematics teaching and learning at a number of levels. So let's start. I'm going to start off with some hard questions. That was not my judgment, it was the judgment of a teacher that I was talking to in the days when I was doing my PhD and I was learning what it means to be a researcher. And so I've been working with this teacher for some time, and we were on our way to his lesson, and he'd been telling me about what he was doing with the students in that lesson. And then he said, as you can see it here, if today's activity doesn't get them there, I will try and develop a different activity that will get them there. And so I asked, what does getting them there look like? And how will you recognise it? And he said, all I can say is I wish you wouldn't ask. We had built up quite a good relationship at this time. But for me it was a naive question. But for him it was a hard question because it was hard to get into the thinking mode that would allow him to really answer it. And of course, he did answer such questions, and in that respect, he was a very good person to work with. So this is my structure for the talk. The numbers are the slide numbers, and I hope I've managed to get through them. There's a bit, third one up, theory interlude, and if I'm desperate, I'll miss that out. But basically, I'm going to be talking about the use of an inquiry approach to learning and teaching mathematics and mathematics teaching, and the relationships between those, and then finally the formal research process that can look into all of that. So, as you could have seen there, I'm starting off with raising some questions, so here we go. Here are some basic questions, I think, for the teacher. So if we think of ourselves as teachers, because looking around I imagine most people here are teachers at some level and in some form, and ask the question, what do our students learn? And is it what we want them to learn? And indeed, what does it mean to learn? Well, I know, of course, that there are lots of theories of learning, and it's not my purpose today to start going into those, although addressing theory is something that I like to do. But we can ask those questions without necessarily saying what we're talking about learning. And of course, here we're talking about learning mathematics or learning mathematics teaching. And so sometimes we have conversations about teaching and learning where we mean teaching and learning mathematics, but we never mention mathematics. So I want to look specifically at mathematics. And of course, these are not only basic questions for the teacher, they're also questions for the researcher into learning and teaching. And so I borrowed this little picture from the internet to ask the question, where is the mathematics? And you can see there it represents the teacher in a teaching learning setting with some students, and you can imagine your particular setting represented by that. So where is the mathematics in our teaching and learning settings? Is it in the teacher's head? On the blackboard? In the textbook? In the classroom? shared by all. And you might have some, I mean, I haven't got there in students' heads, it's only like it to be, isn't it? So, if we think of ourselves as a teacher, with a cohort of students and a mathematics curriculum, I'm still asking questions. How do you get them there, to use the colloquial expression? And how do you know if you've got them? And what if you haven't? What do you do next? Try something new? And then maybe ask, did it work? Sometimes if you try something new, it's actually worse than what you've done before. And what might you do differently? Well, there's a lot of you in there, and it sort of implies that the teacher is on their own working alone with all these questions. But of course, fortunately, that's usually not the case. So can we learn from others? Can we collaborate with others? Help research help, or a researcher, or perhaps teacher researcher. So I said I was going to ask a lot of questions, and here are some more of those questions. What I'm trying to do at the moment is just set the scene for what I'm interested in here. So these questions prompt us to think about the development of teaching as it relates to the mathematical learning of our students. And I know as teachers we do this every day in our teaching lives. And my focus is on developmental research. So we're talking about development in teaching and learning. So just a word or two what I mean by developmental research. And here's a very, very short definition, if you like, of developmental research. It is research which both studies the developmental process and simultaneously promotes development through engagement in question. And that's very important for me. It has this twofold purpose. So you might have a project which is doing the first thing, studying the developmental process. You might have a project which is promoting development through engagement in question. But when I think of developmental research, I mean both of these at the same time. So just an example, this is back to Oxford. We were talking about where I've been in the past. I spent 10 years at Oxford, and I had a project there called the Mathematics Teacher Inquiry Project, and I had money enough to run it for a year and pay for teachers to come out of their classrooms to meetings where we could discuss development together. And at the end of the year, when the money had run out, the teachers were so pleased with the project that they wanted to go on for another year, coming to meetings in their own time. So I thought that was an indication of success. But I've put this in here because of a statement that one of those teachers made at the end of the first year. So you can read, Alex made this statement. So in the project, we were talking about developing teaching. The teachers were engaging with questions. Questions again. Questions in their practice, which they would look into in inquiry ways with support from my colleague at the university. And so what he's implying there is that normal, shall we say, good teaching involves research. Perhaps something that we might call informal research, which is sometimes not really recognised as research by very formal researchers. So it begs the question of what exactly do we mean when we talk about research. And the teachers in the project were much happier talking about engaging with inquiry into their teaching than doing research, because they felt they didn't really know what research was, and I'm not sure if I would know what that's like. So what is research? Well, I've taken a definition here from Lawrence Stenhouse, who was a highly regarded educator in the UK some years ago, and he said, very, very briefly, research is systematic inquiry made public. Isn't that nice? So research is inquiry. Yes. The inquiry has to be systematic, and the results have to be made public. So there's this important thing in the middle here, inquiry, and we can see that as a key word, a term, or a concept. I'm talking about it as an important concept in the whole business of doing developmental research. And systematic, I believe, includes being rigorous, because if we're going to do good research, we want it to be rigorous, and making it public can be at the level of dissemination of colleagues in your own place and in other places, and importantly, it can publish in research journals. So that's research depending on something, a concept called inquiry. So what is inquiry? Well, inquiry is a very fundamental question, and I've been asking a lot of questions so far. But of course, it's not just asking questions. We want to seek answers and find solutions to those questions. So it's this process of engaging with whatever it is in a questioning way, seeking answers and solutions. And these inner words come into it: exploring, investigating, conjecturing, trying out ideas, possibly and hopefully with problems, building on what we know already, not being satisfied, challenging things that come up, testing things that come up, testing conjectures, and overall looking critically at what we're doing. And this word critically is going to keep coming up. I don't mean negative criticism here. I mean really looking into and searching out for the nub of what we're finding here, and modifying what we do if we're not satisfied with overall developing. So developing is where we're heading for. And where is all this taking place? Well, in doing mathematics and in doing mathematics teaching. So the whole business of questioning and seeking out and investigating is both in mathematics, doing mathematics itself, but also in the process of doing mathematics teaching. So, we're building up all of these words here. In teaching, learning, research, practice in mathematics, and inquiry involves, for me anyway, inquiry in 3 layers. And so the central layer to all of this is doing mathematics in the classroom, lecture, tutorial, workshop, wherever, seminar. And the second layer is about teaching practice. So in designing, implementing, and developing teaching practice. And then, yes, it's the third layer. And the third layer is looking critically at the teaching process and developing it systematically, rigorously, and conceptually. So I'm going to be talking about these 3 layers and giving some examples. So let's start off with the first layer, which is inquiry in mathematics. So this is about engaging with mathematics in creative and exploratory ways, and through this, developing appreciation of mathematical concepts and an ability to think mathematically. That's an easy obvious when you say that. And I've got a very nice quote here from one of the fathers of mathematics education, Hans Freudenthal, who wrote back in the 1970s, "It's a not so new, but still rarely fulfilled requirement that mathematics is taught not as creative subject, but as a subject to be corrected. And for me, that fits really well with the notion of engagement and inquiry in mathematics and in mathematics teaching. So, we're at the first layer, the central layer, inquiry in mathematics, and I've got two examples. And the first example is about students in secondary education and a number of teaching goals. These are the goals of the teacher who is teaching these students: to provide opportunity to engage with the topic, stimulate language patterns and imagery, to provide a need to practice and apply procedures, and to promote students' own exploration and inquiry. And there's a lot of stuff in the literature which suggests that these are very important goals to have for working with our students. And the mathematical topic that we're working with here is area and perimeter, and particularly focusing on perimeter. So we're interested in students' engagement with mathematics, using investigation and task activities in mathematics lessons to promote students' mathematical engagement. And this was actually the focus of my PhD long ago, and what I'm going to show you now dates back to that time. We're looking at a teacher called George, and he has a task which he calls 4-square perimeter. And the task that is set to the students is, what perimeters can we get with 4 squares placed edge to edge or corner to corner, but not over. And if you've done it for 4, try 5 or 6 or 10 or 99 or whatever. And so we're looking at shapes such as that, where 4 squares fit side to side, corner to corner, but not over. And he asked 2 further questions: what is the smallest perimeter, and can we find an odd perimeter? And we're coming into the classroom where the class has been working on the basic task, and they've come to the conclusion as a whole class that all the perimeters are an even number. So hence the question, can we find an odd perimeter? So now pray that this works.
What is it about that makes it the smallest perimeter?
Because we're using as few sides as possible, you're only using like 2 sides each square.
So with 5, you just sort of have to, make the square first and then sort of put it on the end.
On the end, yeah. Would that be the best way with 5 squares? Or with a straight line of 5? Would that, which one would you do?
Straight line of 5.
Just try quickly to see if you can work it out. What if you try the half squares? Right? Everyone, just try 5 to see if what you said just now is actually works. Alright? I'll come back in a few moments.
12 is nice. And then you can put this 5 on the end. You stick it on the end.
This one is the longer.
Yeah, because you're using this one.
How many you get? 2, 4, 6, 8. And 2, 4, 6, 8. 10. Do you count it as halves?
Let's add it as a half.
I think it's still... Because look, because you've got the 2 halves and they make 1. So it's still going to be the same, isn't it? And if you put it, because you've got the 2 halves and the other halves that make 1. So, because this will be, let's start there, 2, 3, and there's 4, and then there's the half. That makes it 4. Right, no.
Have you got one side too?
Yeah, because I've got all these halves. Count how many halves on side. So count how many? 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13. And then, yeah, wait. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
So you can, if you have a number of halves. Yeah, if you have a layer, you can have 6 halves adding up to 3. Yeah, so it contains the odd number.
That means if you had 4, that using 4, you can make loads of them.
Yeah.
Yeah, that's cool. So you can make odd numbers if you use halves. What do you use halves? Yeah.
Right, yes, now.
You can get odd numbers, that's 13. That's 13.
So if you have 6 halves, then they add up to 3. So you can make
Hang on, let me start there.
What? There's 1,
1, 2, 2.5.
No, you count the whole sides and then add the
All sides?
Yeah.
What, 16?
No, count all the whole sides.
Oh, all the whole sides, that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah.
Half sides. 1, 2, 3, 4, 5, 6, 8. Well done. So it's got to be a side to side or corner to corner to make an even, and you always get an even number perimeter. I mean, why is...
So, I think you might say that thinking about those inwards, that there's some investigating, exploring, some of those things I mentioned earlier. But anyway, here were the goals. To provide an opportunity to engage with the topic. Did they do that? To stimulate language patterns and imagery. To provide a need to practice and apply procedures. I think so. And to promote students' own exploration and inquiry. So we're okay on the goals. And looking at what they've achieved, well, they started off from this position of having looked at a wide range of shapes that they could get and finding they were all even. They've actually come up with one. It doesn't contradict the original rules because they don't actually overlap. So they've found an odd shape, so they have done it. They've answered the question that was set. So, I feel fairly certain that these girls know what perimeter is. Whether they're going to confuse it with area later, who knows, because we know that that's something that students do. We can see from what they've done that they were trying out special cases, making conjectures, and moving towards generalisation. Well, maybe they were moving towards generalisation. They were certainly engaging in mathematical thinking. We can ask to what extent do the students' examples only special cases, or whether indeed they are generic. So this set that adds up to 13 for the perimeter, can you do the same with 5 squares or 6 or however many? We don't see that, and we don't actually know what they did next. And that leads us to what would it take for those students to produce a proof. So perhaps the stage that they're at is still quite a long way from proving something. But on the other hand, they weren't asked to prove something. They were asked, could they find a case with an odd perimeter. We'll be coming back to this a bit later, so let's go on to the second example. This time, the students are first-year university students in a materials engineering program. And this is part of a research project that we had at Loughborough called Engineering Students Understanding Mathematics, with some money from the Higher Education STEM program. And we were a teaching team of 3 people, 3 experienced teachers, 2 of them experienced with teaching engineering students. And what we did here was to design a 4-fold teaching innovation. Looking back, I think we were fairly bold. And these were the elements in that teaching innovation. We were using query-based tasks, small groups and tutorials, and the course had 2 lectures and 1 tutorial each week for 15 weeks. Computer environment, we used GeoGebra, and an assessed small group project. So it wasn't just small groups discussing things, they also had to do a project and hand it in for assessment. So what were the goals here? Well, to provide opportunity for students to develop conceptual understanding. What was quite clear when these students came to us from schools was that they were turning the procedural handle. They wanted everything to be set out very clearly, step by step, and they would go through the steps, and they would therefore be doing mathematics. And we felt there's more to doing mathematics within an engineering course than that. So we wanted to develop some level of conceptual understanding. We wanted to stimulate awareness of alternative representations of functions. The students that the materials engineers accepted onto this course were in many ways poorly prepared for university mathematics. So we were covering a lot of mathematics that we would expect to have been covered at school level and wasn't. To promote students' own exploration and inquiry through the use of GeoGebra and of course the inquiry-based questions, and to develop students' capacities to reason and analyse, both of which are important for engineering practice. And this was discussed with the engineers. We had one of them in a small advisory board with us, advising on the project. So we're going to look at a particular task that was used in this work with students. It was started off in a lecture and then continued in the tutorial, and it was about functions and equations. So there's the first bit of the A part. Okay, so this was given in a lecture, and the lecturer asked the students to engage with this question there and then, in singles, pairs, or small groups in the lecture theatre, and to come up with their own answers to question A, and then invited students to tell her what they came up with. And I can't remember whether it was written on the board or not, but to notice that there were different answers, and there was a bit of debate about whether they were right or wrong. So in the tutorial which followed, so in the lecture we saw part A, and in the tutorial which followed, they were given a sheet which had the whole task on it, A, B, C, and D, and they had to engage with this. So you can see that the task is designed to start off, not exactly procedurally, but at least fairly simply, so that the students could get a grasp of what they're being asked to do here with a fairly straightforward function and thinking about relationships between the function and the graph and the lines crossing. But you can see that when we get into this part of it, it's really quite a lot more demanding. And it's asking the students to explore, investigate, come up with their own possibilities and look critically at what they're getting here. Now, I don't have a video in this case, so please imagine. So small groups, approximately 4 students, some 3s, maybe a few 5s, around 50 students in total, engaging with inquiry-based tasks in a computer lab, so that on the computers they could get GeoGebra. And they were expected, and they've been told this, of course, to explore the task seriously, using GeoGebra, and in their groups to discuss mathematically what they were seeing and finding. and the tutor and the graduate assistant circulated, talking to each group, discussing mathematics with them, and in some cases challenging them to look more critically, look beyond what they've done so far, and asking questions to enable that to happen. So you're imagining this, think to yourself, what do you think this discussion looks like, and what do you think the two tutors are doing? You're probably not surprised to be told that in some groups the students were engaging in ways very much like the expectations, and the tutors were talking with them, and it was all coming out really well in terms of what the expectations were. But in others, students were playing with GeoGebra, filling the screen with loads of functions and making coloured pictures, but not much more. And in other groups, there was emailing and Facebook and what have you, until we came around and started to do mathematics. So there was some good and some not so good. But these students, we have to recognise, were not used to this kind of activity. And also, they were not used to the sort of freedom that this was giving them when they'd been used to turning the procedure at home. Now, we had a researcher working with the three of us, and she was observing, watching tutorials, interviewing the students, bringing back data, field notes and audio recordings, and the teaching team, three of us, and researcher were analysing the data and reflecting on its messages for the programme as it stood now and for future teaching. Well, we had a lot of data, and in the time I've got, I can't possibly start talking about this in general, but I thought you might be interested to see some of the student perspectives. And this first one, we set every group a project which they had to do in handling for assessment. And in that project, one of the things we asked them was how GeoGebra had contributed to their working project. And this was one of the responses. And we looked at that and thought, okay, good. But of course, they're handing in a project for assessment. They're not going to tell us that's good use of GeoGebra. In the focus group interviews, after the teaching finished, this was what came from one of the students in the first focus group. And we might say, well, that student just hasn't got it. Whose fault is that? And what about this one? So, the left-hand one and the top one make us think that at least some of the students understood what we were trying to do in this project. But nevertheless, because there was an exam at the end, many of the students were saying that they hadn't done practice for the exam, and the inquiry base had allowed them to do this exploration, learning for exploration, but they didn't have the procedural steps to work. So, we'll come back to this as well, sure. In both of these examples, the school and the university level, research shows us areas of achievement with regard to teaching goals, and also highlights areas for improvement. Well, that's not particularly surprising. It's nice that there were some areas of achievement. And as teachers, we learn from critical observations which are backed up by research evidence, because of course we were analysing our data as rigorously as possible, although there was rather a lot of it, and we didn't get through every bit of it. And the awareness of areas for improvement can lead to teachers taking action to improve. So this is a very important aspect of a project such as this. What we learn from it, even if we're not terribly happy with what we see, at least that gives us something as a basis for improvement. So, for example, in the school one, George might ask future students to try to prove their conjecture. He might ask questions that are a bit more demanding than just finding the case. And the university teachers might look critically at the role fulfilled by the examination. And of course that's tricky because it's both departmental and university-wide policy to have this kind of examination. So we come to the second layer in the three layers, which is inquiry and designing and implementing teaching practice. So when teachers recognise questions and issues in their teaching, as I was just saying for the second example, it provides opportunities for them to explore, innovate and improve teaching practice. And one way to do this is through the use of inquiry-based tasks, as I've been showing here. But there are alternatives to that, to inspect practice, reflect critically, possibly with colleagues, leading to insights for development. One of the things I wrote not so long ago, in fact, when I was asked to give a talk somewhere, maybe this is a very obvious thing to everybody, but it took me some time to recognize. One of the main things I've learned over the years is that developing as a mathematics teacher requires one to be alert. Now, that's not so remarkable, clearly, but when you're a learner, you become an inquirer, or you can become an inquirer. And so the learner-teacher, so you're not just the fount of knowledge offering it to students, but learning from the whole process is an inquiry stance. This is just a little reflection from, in fact it was the Eason lecturer who wrote this after one of the lectures. And it was in giving a particular question in the lecture and seeing that students responded to it in different ways, and then when asked to tell what they were seeing there was actually dialogue across the lecture theatre. And in the past there had been individual responses, but not in the lecture dialogue. So that was a very good experience, and then therefore it raised the question, what kinds of questions can we ask that are going to result in that kind of experience? So, thinking back to our two examples, the George lesson, after that lesson, the school mathematics department met to look at George's video. So they were together viewing the video and discussing teaching. And George himself reflected openly with his colleagues. And here are two of the things that he said. I was ad-libbing. I didn't know what would happen for half squares. So the girls had come up with these half squares, and George didn't know what the outcome was going to be. And so he says the girls were teaching them something. So he was certainly learning from that activity. And then the colleagues were both supporting George, being respectful and sympathetic to him, but at the same time asking questions and making suggestions. And the question of proof came up. What would it take to get those students working towards a proof? And that was discussed in the group. So again, engagement with this sort of discussion with colleagues enables teachers to go back to their teaching with new ideas. So, through inquiry and practice, in collaboration with other colleagues, and I was there as an outside researcher, George develops his own teaching. I mean, we don't see that here, but I know from other things that happened in the project that he went on to try out new ideas. The discussion of issues within the mathematics department leads to departmental development. So it was beneficial also for the colleagues who learned from the discussion and the issues raised. And then I've put up here recall data, because those of you who know about and have been involved in data might see parallels between what I'm talking about here with George. And so just a word about the Dayton project. So there, as I understand it, a group of mathematicians met regularly to discuss teaching, viewed video on one of their lectures, which the lecturer had chosen, discussed the extract, and in doing so, talked about different factors and issues in teaching. And in the Dayton project, I understand that the lecturers who were taking part were drawing on Schoenfeld's ROG theory, identifying resources, orientation, and goals in their teaching. And in doing so, of course, recognising ways that they might address their teaching. And in connection with that, and I'm working with Tanya now, and Tanya has just got a group together to start to engage with Dayton 2, and I saw more or less what I've described here for George and colleagues with the mathematicians in Dayton 2. So that was a very nice experience which I appreciated having, and we're going to continue with that project in collaboration with colleagues. I'm going to skip this one because time is running. So, central to inquiry then is the asking of questions, particularly critical questions, which challenge the status quo and make us start to think differently. Finding answers to the critical questions would be ideal, but I think it's rather in addressing such questions that we start to see possibility for changes in practice. So it's not that suddenly a question pops up and we think, oh, that's a good question, and we go and find an answer to that question, because that's hard. Coming back to the idea of hard questions. Sometimes the issues that are thrown up, like the problem with having a very formal exam at the end of the engineering mathematics course, was seriousseriously problematic, but we couldn't easily just go and change that. So we had to think of ways in which we could develop the idea of having an exam to match more clearly with what we were trying to do. In all of this, I suggest that as we engage with inquiry processes, whether it's in mathematics in the classroom, or whether it's as a group of teachers inquiring into teaching, or both, we are developing an inquiry stance or an inquiry way of being. So if we start using inquiry just by asking a question and seeing how we can approach trying to answer it, or by using an inquiry-based task, we might be seen to be using inquiry as a tool to enable us to look critically at our teaching. But over time, when we are doing this familiarly and regularly with our colleagues, we develop an inquiry way of being. And Wilco and colleagues talk about that as MEU habits of mind. It becomes a habit, it becomes the way that we do things. Now, I said that I would skip this if we were running out of time, so I just want to... So, here we are with inquiry in 3 layers, as I've been talking about, and together they form a model for inquiry-based teaching and learning. So at the centre of the model framework that we have here are students engaging in inquiry in the classroom. Around that, because I think the nesting fits very well with the notions of the relationships here. So the second layer then, teachers engaging in professional inquiry to learn more about creating mathematics opportunities for students. And then researchers inquiring with teachers to promote professional development and learn more about practical implications and issues for mathematical development, and engaging in serious research at that level. We're looking at that in its full sociocultural complexity, so we're not just looking at what's going on in the minds of students and teachers, we're taking into account the institutional setting that's involved. And we're thinking of partnerships between researchers and teachers, and those partnerships are fundamentally focused on students' engagement in the classroom and better understanding of mathematics. And the whole three areas there form an inquiry process that is linked across the levels. So, at the moment, at Loughborough, we are part of a European project that is known as Platinum. We have teachers and researchers in 8 universities in 7 European countries, taking this model as a basis for our activity, and we're developing communities of inquiry in professional development of mathematics teaching, and the design of inquiry-based tasks, and a number of other possibilities. And it seems to me that this is very like what we're trying to do with Data 2. At least I think Tanya agrees with me on that, although there might be slight differences. So I'm hoping that we can bring the group here into this Platinum project in some way and really work together on that. Now, I realise the time is long and I've got several further slides. We wasted some time at the beginning. I am going to stop and have questions, but what if I had time for these slides? They're going into the research process, and what you've got in front of you there is from the ESOM project. It's an extract from a paper we wrote where we're using activity theory to juxtapose the two cultures in that project. The culture of the teaching team using innovation to engage students more conceptually with mathematics, and the students coming from school where they've had a procedural background and not being yet ready to really take on what we mean by this inquiry-based activity. And by looking at these through an activity theory approach, we're able to say something about what it is that we're seeing here in these differences, and how we can look at this further in the whole institutional context. So I'm going to stop there. Thank you.
We do have time for a few questions.
Because you were talking about the procedural versus like the conceptual, what you're trying to do with the engineering students. Do you think like there's a bit of a cap on inquiry when you're teaching, when students are only there to learn procedural mathematics, if they're using it for another subject and they're not actually becoming a mathematician? Like when we're approaching mathematics education research, is there, not less point, but is there less to be gained from trying to research those sorts of students who already have preconceived ideas about mathematics? And
Well, they come from school classrooms where they've been in the same culture as those who go on to be mathematicians at university. But we talked with the engineers about what we wanted to do and whether they felt this applied to engineering. I mean, we were not trying to teach mathematics through a proving process because we didn't feel that that was relevant to the students. But nevertheless, we wanted them to engage with mathematics. I mean, just take functions, for example. It became clear to us that really they didn't have a very mathematical notion of what a function is and how the relationships between different representations, they would look at a graph and just see it as an object, and the object came from the formula that they wrote down, y equals something x. So by looking at representations of functions in a more inquiry way, we felt that we were engaging the students in a way that helped them to come to a more relational understanding, more conceptual understanding. And the engineers, you probably notice where I said that we wanted them to be more analytic and analytic and reason about what they were doing. Suited the engineers very well because that's what they're trying to achieve with the engineering.
Is there a possibility, do you think, of the exam format changing with those sorts of movements that you're making with courses like that?
Well, I hope so. But here again, it's both an institutional thing and a departmental thing. And it's across two departments. So, there are all sorts of factors beyond just the wish to change the exam for it to be more appropriate to the nature of the course. But in the way that the Dayton project is working, we have an inquiry group with people from mathematics who are teaching engineering students and other groups. And through developing the ideas here, we can start to bring in possibilities for changing the nature of the exam. And one of my colleagues is looking very closely at oral examining as an alternative to a formal examination.
One more question?
I'm just wondering if you think that some of the difficulty that you have with that kind of project in engineering departments, which is engineering students have is that it's not just the expectation of the students, it's actually the expectation of the rest of the engineering staff as well, and that their view of mathematics is quite procedural.
We didn't explore the views of the engineering staff because it wasn't a big enough project to do that. We were looking at the mathematics team and how we were thinking about designing the tasks and activity with the students. But with more time and resource, we could have done some exploration, especially with the engineering staff as well. So we were able to do.
Once again, thanks to Professor. Just to highlight something, we're not putting people in Loughborough in different temperature extremes, and Matthew in a sweatshop, but you're in a refrigerator. It's not good about that. Next week, Wednesday, we have